All right, section 6.7 gets into taking a look at the equations of a polynomial and graphing them and identifying certain features of the graphs. Now, to begin with, the look of a graph is determined by the degree of the polynomial. Now, if you can, make this little chart. If the degree of a polynomial is 1, for instance, y equals x plus 7, that would be a degree of 1. It is a linear graph that looks like a straight line. We've learned that from Unit 2 and Unit 3 this year. If its degree is 2, that means it's a quadratic equation and it will make a parabola. If the degree of the polynomial is 3, it will make a graph that has a bend in it that looks something like that. That is called a cubic equation. If the degree is 4, then it's going to look something like a W. And that is called a quartic polynomial. And finally, if its degree is 5, it's going to look something like that, which is called a quintic polynomial. So the degree will always tell you the look of a graph. And if you can kind of put and associate the degree and what the graph looks like, that will be good. And we're going to mainly talk about degree 3, 4, and 5 as we go through units or section 6.7. Now, what's important about a graph is its end behavior. The end behavior is a description of the values of the function and specifically what happens at each end of the graph. When you describe the end behavior, you read it like a book. Pretend you're a little bug tracing the graph from left to right and describe it. So for example, down at the bottom, here's a graph, and if I ask you what is its end behavior, what I do is I start on the left side of the graph. This is the left end of the graph, and I call this up because the graph is going up from that side of the graph. Now, if I trace it all the way to the right to its final end, at the very end I'm going down. So I would describe this particular graph's end behavior as an up and then down graph. Because at the left side I'm up and at the right side I'm down. So I hope that answers your questions and describes what end behavior is. Now, very important and the most important part of this section, the degree of the polynomial and the lead coefficient will determine the end behavior. Number 1, look at the degree, and number 2, look at the lead coefficient. We're going to make a chart. So if you want to pause the video and make this chart, we're going to make a chart that has the degrees. On top is odd degree. On the left side is odd degree. On the right side is even degree. And down the columns are going to be the lead coefficient. This is if the lead coefficient is positive. This is if the lead coefficient is negative. Now, how does this work? Well, let's talk about the situation where your lead coefficient is positive and it's an odd degree. Your graph, if the lead coefficient is positive and it's an odd degree, your graph will look something like this, which its behavior is down and up, because it starts down and it finishes up. For these particular graphs, the domain is all real numbers, and your range would be all real numbers. So if the lead coefficient's positive and it's odd degree, your graph will look similar to what I described. If it's an even degree and the lead coefficient is positive, your graph will look something like this. It will be up and up would be its end behavior. And in this particular case, again, the domain will be all real numbers. However, the range is going to be all values, whatever they are, all values have to be greater than or equal to whatever the minimum is. The minimum being, for instance, this point right here. All the range or all the numbers on the red graph are higher than that. If your lead coefficient now is negative, let's consider this case. If your lead coefficient is negative and you have an odd degree, it's basically like the graph is flipped the other way. So when your lead coefficient is negative, this will now be an up and then down end behavior situation. Again, the domain is all real numbers, and your range will be all real numbers. And finally, if the lead coefficient is negative and it's an even degree, then your graph is going to be flipped the other way, something like that. This would be a down and a down situation for your end behavior. Down and down. Your domain, again, is still all real numbers. However, now your range is going to be all values less than or equal to the maximum. For instance, right here where my x is would be the maximum value, and all numbers are below that for your range. So now, if you need to pause the video, please do, because then I'll look at two examples real briefly and we'll be done with end behavior. All right, let's practice. Here's a polynomial, and let's say we were going to graph it. Well, before we can graph it, we got to identify the lead coefficient, the degree, and then determine the end behavior. Well, first of all, it is degree 5. This is odd. So going back one page, we are in the odd column. We look at the lead coefficient. The lead coefficient is -2. It is negative. So we are in the situation where, if I go back a slide, we are negative and odd. That means our end behavior of this particular polynomial, the end behavior of this would be up and then down. So when we graph this, this graph has to look something like this, because it's up and then down. One more example. I gave you a graph. Now, you need to determine, first of all, is it an odd or an even degree? Well, this is a situation that is down and down. So if we go back to our handy-dandy chart way back here, down and down is right here, which means we are an even degree. So therefore, this degree of this polynomial, whatever it is even. Letter B, what is the lead coefficient? Well, since it's down and down, if I go back to my chart, down and down, the lead coefficient is negative. So if I was to write my polynomial, it would have a negative lead coefficient. And people, that is the connection between degrees, the lead coefficient, and what the graph does at the very ends of its graph.